Hey everyone, and welcome. Today, we're going to pull back the curtain on one of the most fundamental tools in all of data science, linear regression. Now don't let the simple name fool you. This thing is an absolute powerhouse. At its core, it's all about finding the hidden story in your data so you can make some really smart predictions about the future. So let's dive right in. I want you to imagine something for a second. You're looking at a house, and the only thing you know about it is its size, the square footage. Now what if you could take just that one number and make a really good guess at its price? That's exactly the kind of puzzle linear regression was born to solve. It's about taking what we know to predict what we don't know.
So how do we actually make that prediction? Well, we use this amazing technique called linear regression. Let's get properly introduced to this incredibly powerful tool. At its heart, linear regression is a type of supervised machine learning. Now, all that means is that we teach the model by showing it a bunch of examples where we already have the right answers. Think of it like a stack of flashcards for the machine. We show it a bunch of houses with their sizes and their actual selling prices, and it starts to learn the relationship between them. And this is where it gets really cool. Check out how flexible this is. With simple regression, we're using just one input, right? Like house size predicts price. But with multiple regression, we can start throwing in more factors, like what about the number of bedrooms or the age of the house? And then there's polynomial, which lets us model a curve in the data, not just a straight line. And you might be wondering, why is it still called linear then? Well, it's because the math behind the coefficients, those b values, is still linear, even if the line itself is curvy. Pretty neat, huh?
Okay, so if you picture all of our data points on a graph, you could draw, literally an infinite number of lines trying to cut through them. So how in the world does the machine learn how to pick the one single perfect line? Let's figure that out.
The goal is actually really straightforward. Find the one line that has the smallest possible error. We're on a mission to find the line that, on average, gets as close as it possibly can to all of those real data points.
And how do we measure that error? With this little thing called the sum of squared errors, or SSE. It's brilliant. For every single data point, you measure the distance to the line. You square that distance, and then you add them all up. So why do we square it? Well, squaring the error massively punishes the line for any predictions that are way off. It basically forces the line to care a lot more about those big mistakes, which helps it find a much better balance overall.
But here's the catch, and it's a big one. Linear regression is not magic. For the results to be something you can actually trust, your data has to play by a certain set of rules or assumptions. If you break these rules, your model could give you results that are totally misleading or just plain wrong.
Now, here they are, the 6 big assumptions. Don't get overwhelmed by the list, though. While they're all super important, we're going to zoom in on 2 of the most common ones you'll run into, multicollinearity and homoscedasticity. If you can get these 2 right, you're well on your way to building a solid model.
Let's talk about multicollinearity. This is a big one. It happens when your input variables are basically telling you the same story. For example, a house's square footage is probably highly correlated with its number of bedrooms, right? Bigger houses tend to have more bedrooms. When this happens, the model gets confused and has a really hard time figuring out how much each variable is contributing on its own, making your results unstable.
So, what do you do about it? Well, it's a pretty clear process. First, you have to find it, using something like a correlation matrix or a VIF score. Once you've found it, you've got options. The simplest is to just remove one of the variables that's causing the problem. Or you could get clever and combine them into one feature. And if you want to get really fancy, there are advanced techniques you can use. Okay, next up is a word that is an absolute mouthful, homoscedasticity. But trust me, the idea behind it is so important. What we want is for our model's mistakes, the errors, to be random and spread out evenly. That's homoscedasticity, and that's good. It means our model is just as reliable for small houses as it is for big mansions. The opposite, heteroscedasticity, is bad. That's when your model might be great at predicting cheap houses, but terrible at predicting expensive ones. That makes your model totally unreliable.
All right, so we've built our model. We've checked the assumptions. The big question now is it any good? How do we actually grade its performance? How do we know if we've built a superstar or a total dud?
Well, we use performance metrics. The most famous one is R-squared. You can think of it as a percentage that tells you how much of the story your model is actually explaining. A high R-squared means your inputs are doing a great job explaining the changes in the output. Other metrics like MSE or MAE are more direct. They just tell you, on average, how wrong your predictions are.
But there's a sneaky little problem with the regular R-squared. It will almost always go up if you add more variables to your model, even if those new variables are completely useless. This leads us to a really important question. Which R-squared can you actually trust?
And the answer is adjusted R-squared, especially when you have more than one input variable. This is the number you want to look at. It's smarter than the regular R-squared because it actually penalizes you for adding in extra features that don't really improve the model's predictive power. It keeps your model honest.
Okay, we have covered a ton of ground, so let's boil it all down into a handy little toolkit. These are the absolute must-knows, the essentials for your next project or, that big technical interview.
If you're in an interview, these are your lightning round answers. What's the cost function? SSE. How does it optimize? Usually gradient descent. Why do we square the error? To punish big mistakes. What happens if you have too many features? You get overfitting. And how do you fix that? Regularization. Nail these, and you'll sound like you know exactly what you're talking about.
And that really brings us to the big takeaway. If you remember just one thing from all this, let it be this. Linear regression is all about finding that one best line by making the error as small as possible. But its real power is only unlocked when you follow those strict assumptions. Master these concepts, and you are well on your way to building some incredibly powerful and reliable predictive models.